Korea, in Seoul? Yeah.
Organizacija ovog skupa je kao i uvijek ispred Hrvatskog geotehničkog društva. Ja zahvaljujem upravi društva koja podržava ovu akciju i da smo danas svi ovdje zajedno. Zahvalio bi i našim suorganizatorima, Tehničko veleučilište u Zagrebu, prije svega profesor koja je svojim velikim angažmanom kao i uvijek pridonijela organizaciji ovoga skupa. Zahvalio bi našem domaćinu, Rudarskom geološkom naftnom fakultetu, koji nas je opet lijepo ovdje ugostio i osigurao nam uvjete za današnje predavanje. Naš današnji gost je profesor Atilla Ansal, dear guest, profesor Atilla Ansal. He's coming from Istanbul, Turkey, and he will present us a presentation titled Seismic, Microzonation and Earthquake Scenarios. Imat ćemo prezentaciju po modelu engleskog prijevoda na slajdu kako bi mogli pratiti kolege na taj način. Vrlo smo zadovoljni sa odazivom, evo preko 150 prijava smo dobili putem internet obrasca. Većina nas je ovdje, neki nas prate i preko prijenosa uživo. To nam je osigurao opet ekipa iz Tehničkog veleučilišta u Zagrebu i dostupno je na internet stranici HGD-a, vjerujem da nas kolege prate. Osim nas, članova Hrvatskog geotehničkog društva, kolega koji svakodnevno surađujemo u području geotehnike, ja bih htio pozdraviti predstavnike naših znamenitih institucija koje su se priključili danas u ovom našem skupu, pa bi pozdravio predstavnike Ministarstva graditeljstva i prostornog uređenja, Hrvatski zavod za prostorni razvoj, Državnu upravu za zaštitu i spašavanje, Hrvatsko gorsko spašavanje, Geofizički odsjek Prirodoslovnog fakulteta Sveučilišta u Zagrebu. Naime, tema današnjeg skupa je vrlo široka, puno je djelatnosti uključeno i međusobno povezano. Mi smo samo jedan segment u zapravo nekakvom sustavu koji vodi brigu o potresu, bilo u izučavanju potresnog djelovanja, definiranju podloga i kasnije sprječavanje šteta koje od toga nastaju, pa i rješavanje posljedica kada se potres dogodi. Dakle, sustav je cjelovit, pa evo zahvaljujem svima iz drugih institucija koji su se priključili kako bi se podružili, upoznali i cjelovito djelovali. I would like to welcome our colleagues from Vienna, University of Technology, that came today, and their colleague also from University of Utah. Zahvalio bi dolasku naših kolega iz društva za mehaniku tla i geotehničko inženjerstvo koji nam dolaze sa fakulteta za gradbeništvo i geodeziju, Univerza u Ljubljani, Zavod za gradbeništvo Slovenije. I također kolege Srpskog društva za mehaniku tla i geotehničko inženjerstvo koji nam dolaze sa Zavod građevinskog fakulteta, Instituta za istraživanje materijala, Rudarskog geološkog fakulteta u Beogradu. Evo, još jednom svima veliko hvala na ovom odazivu. Nadam se da ćemo dobiti lijepi uvid u problematiku potresnog inženjerstva od profesora Atilla Ansala, podružit se kasnije na tome. Pa evo, da ja dalje ne kradem nama vrijeme, pozvao bi kolegicu
distinguished ladies and gentlemen, dear colleagues. It is really an honor and pleasure to welcome you on behalf of the Faculty of Mining Geology and Petroleum Engineering of the University of Zagreb and myself. As being the only faculty in the Republic of Croatia that conducts high educational studies in the field of mining engineering, geological engineering, petroleum engineering, in the field of technical sciences, and one of the two faculties that conducts high educational studies in geology in the field of natural sciences, we understand the importance of the issues that will be covered by today's lecture: seismic, microzonation, and earthquake scenarios. Also, through the nature of our occupations, mining engineer, geologist, petroleum engineer, which fall into the category of hazardous occupations, we are fully aware of the necessity of incorporation of safety, security, preparation, and preparedness aspects into all the activities related to nature behavior. Thus, we strongly support the efforts of Croatian Geotehničko Society into organizing such lectures as this one today. Hopefully, the knowledge that you will gain from this lecture and the knowledge that we strive to transfer to our students in this subject, especially throughout our graduation sub-program Geotechnical Engineering, will only be used in protective and preparedness purposes. With these hopes and thoughts, I leave you to the lecture of Professor Ansal. I give you greetings from our dean, who apologized not to be here today due to previously arranged obligations. I wish all of you a successful day and a pleasant stay at our faculty. Thank you.
Nastavljamo dalje. Dakle, prilika je uvijek na našem skupu u okviru Nonveillerovog predavanja prisjetiti se dijela i kazati, znači života profesora Nonveillera, pa bi ja posvetio nekoliko slajdova da se prisjetimo određenih događanja i projekata kojima je profesor sudjelovao. Vjerujem da se čujemo. Alo? Može. Ok. Dakle, profesor Nonveiller pripremio sam prezentaciju prvenstveno iz nekakve baze podataka naše iz Hrvatskog geotehničkog društva na kojoj vrijedno rade i profesor Benić, profesor Brkljan, profesor Savić, dakle i na temelju toga pokušavamo sačuvati sjećanje na profesora. Dakle, rođen je u Trstu 1910. godine, pohađao je školu srednju u Splitu. Nakon toga odlazi u Beč, dakle, gdje završava za građanskog inženjera na Tehničke hochschule u Beču 1932. godine i tu zapravo ima priliku čuti predavanja od profesora Karla Tercaglia, što je značajno utjecao na njegov daljnji rad. 1957. doktorira na temu stabilnost nasipa, nehomogenih nasipa kod profesora Šuktera na Univerzitetu u Ljubljani. Nakon toga njegov rad kreće značajno u smjeru znanstvene djelatnosti. Ako krenemo od 1932. godine, kada je počeo kao mladi inženjer, dominantno je radio u građevinskim poduzećima na niskogradnji, na temeljenjima, problemima zahtjevnih građevina i uvijek u svome životu, dakle u radu, dolazi do pozicije rukovodstva gdje se donose ozbiljne odluke i tako ga susrećemo kao generalnog direktora u hidroelektriji, zatim voditelja geotehničkog odjela u elektroprojektu, geoistraživanju, dakle kasnije u geoekspertu i geotehnici. Profesor je na fakultetu, građevinskom fakultetu u Zagrebu, osnovao je uopće postdiplomski studij geotehnike uvijek je prilika prisjetiti se i upoznati zapravo značajnije projekte gdje je profesor Nonveiller bio prisutan. Ja sam izdvojio sljedeće, dakle, hidroelektrana Vinodol gdje je u samom početku 1999. toga rada radio možemo ispitivanja detonacije stijenske mase, ispitivanjem u tlačnim tunelima prilikom izgradnje. Kasnije su veliki doprinos radu u dijelu naftnih građevina, brana, dakle primjer Lopačke iz 1954. Ali i izvan Hrvatske, dakle Mahabad i Iran 1971. i čitav niz zemalja u kojima je djelovao bilo kao projektant. Jedna od značajnijih i poznatijih je brana Peruča. Evo vidimo izgradnju 1959. specifična po tome što je to bila prva velika akumulacija u kršu. Ona je doživjela i devastaciju 1993. u Domovinskom ratu gdje je profesor opet sudjelovao u sanaciji. Zatim značajni projekti iz područja temeljenja gdje su radovi dospjeli i na međunarodnu razinu gdje su poslije pojedini autori koristili za razvoj raznih teorija. Dakle, jedna od takvih je silos za žito u Rijeci, za promatranje dugotrajnih i velikih stjeganja i spektakularan, da tako kažem, keson reverzibilne hidroelektrane u Brovac, koji je ovako sucesivnim kopanjem tonuo prema dolje. Taj rad je prepoznat kao izuzetan i uvršten u najboljih 10 godina 1987. Journal of Geotechnical Engineering. I dalje, dakle, čitav niz velikih značajnih aktivnosti, od stabilizacija složenih klizišta, od razvoja originalne metode stabilnosti kosina, originalne teorije koja je opisala nesreću koja se desila klizanju brane Vajon, prijedlog sanacije tornja u Pizi i čitav niz dalje raznih događanja. Ono što ostaje, dakle, trajno, to je njegov pisani, dakle, rad sa više od 150 znanstvenih i stručnih članaka, velik broj knjiga koje dan danas koristimo, pogotovo mi mlađi inženjeri koji da nismo imali priliku upoznat, možemo vidjeti veličinu njegovog rada, svakako mehanika tla i temeljenje kao jedna bazna knjiga, a i nasute brane, dakle, klizanje, stabilnost kosina i iniciranje tla. Dakle, veliki opus radova u svim područjima od terenskog iskustva, projektiranja, konzultinga, nastavno znanstvene djelatnosti. Profesor je do 1978. na Građevinskom fakultetu, 1981. ide u mirovinu, ali i dalje je aktivan kroz rad u UBH-u, pisanje članaka i napušta nas 1999. godine. Ono što ostaje je veliko nasljeđe koje je na nama da se čuvamo i na neki način u čast se posjetimo, pa makar ovako kroz godinu barem jedanput. Dakle, njemu u čast od 2000. održava se upravo ovo Nonveiller Lecture, predavanje, koje je prvo održao 2000. profesor upravo sa Tehničkog univerziteta u Beču i nakon toga profesor Verić kao prvi magistar znanosti iz područja geotehnike kod nas u Hrvatskoj, koji je bio, dakle, pod mentorstvom profesora Nonveillera i nadalje čitav, dakle, niz dragih kolega inozemnih i domaćih sve do danas kada smo došli do profesora Atilla Ansala, našeg predavača. Pa evo, nadam se da je malo osvježeno sjećanje, a ja bih prepustio dalje i pozvao profesoricu Sonju da nam predstavi našeg predavača.
Dakle, dobar dan i od mene i evo ja samo ponavljam kratko popis svih ustanova. Skupili smo se ovdje raznih struka, sa raznih strana, raznih ustanova i mislim da je to jedan novi poticaj suradnji i prepoznavanju ovih problema živimo u takvom području i što je arhitektura koju imamo, pogotovo starije zgrade, stariji gradovi, slično ovome što smo imali u Makarskoj, u Zagrebu prije, u Italiji, ovo što se lani događalo u Italiji je vrlo interesantno isto tako. Puno je, međutim, bolnica i škola koje možemo i ostalih zgrada koje možemo pripremiti da im se to ne dogodi. Ovdje je sa Geofizičkog zavoda pregled svih 30.000 potresa koji su zabilježeni ili su prepoznati iz vremena prije nego što se mjerilo djelovanje potresa. Ne mogu ne spomenuti ovdje da je jedan od značajnih osoba u seizmologiji i u bavljenju potresima odavde iz Hrvatske, profesor Mohorovičić, i Geofizički zavod sad posebno obilježava njegovu godinu njegovog rođenja. Na ovom fakultetu objavljen je članak djelatnika ovog fakulteta o posljedicama, nekim posljedicama toga istog potresa u Zagrebu. Dakle, ovdje se vidi gdje je prepoznato događanje likvefakcije u tome potresu. Isto tako označeno je crvenom linijom i područje gdje se može u budućnosti očekivati likvefakcija, što je jedan od ozbiljnih problema kojima se mnogi bave. Potres se često prati i požar, što komplicira situaciju kad je oštećena infrastruktura, zato što vodovodi i tako dalje često moraju prelaziti preko rasjeda, pa onda mogu stradati prometnice i tako dalje. Ovdje je samo ilustracija jednog od mogućih rješenja, dakle ovo rade kolege koji se bave transportom nafte. Dakle, postoje ovakvi klizači kao rješenje da se cjevovodi prevedu preko rasjeda ili sl. I za kraj ovog kratkog uvoda je fotografija iz potresa Kođaeli iz 1999. godine, kada vidimo jedan kontrast zgrade koja gotovo da nije oštećena i ove koja tako dramatično traži, takve zgrade traže ojačanje. Postoje puno rješenja, dakle i mi geotehničari i kolege konstrukteri imamo mnogo rješenja. Imamo kao mogućnost koristiti ugušivače, izolatore, možemo poboljšati to da smanjimo djelovanje potresa i tako dalje, ali je važno da ta rješenja primjenjujemo na novim, a i na postojećim građevinama, dakle u skladu sa uvjetima na lokaciji. I o tome će nam sada kazati profesor Atilla Ansal. Profesor Ansal je sada voditelj odjela za građevinarstvo na, sad ću reći, Sveučilištu u Istanbulu. On je istovremeno i predsjednik Europske asocijacije za potresno inženjerstvo i par riječi, diplomirao je, odnosno magistrirao u Istanbulu, doktorirao je na Northwestern University kraj Chicaga, bio je profesor najprije geotehničkog, a potom potresnog inženjerstva u Istanbulu na više sveučilišta. Postdoc je radio na NGI-u, najvećem geotehničkom institutu. U Tokiju smo se upoznali, bio je gost zahvaljujući JICA ustanovi agenciji i sada vodi to građevinu na tom sveučilištu. Profesor Ansal se bavi potresnim geotehničkim inženjerstvom i dinamikom tla, analizom seizmičkih hazarda, seizmičkom mikrozonacijom, laboratorijskim i ispitivanjima in situ, također ponašanjem tla konstitutivnim modelima i danas će nam nešto od toga pokazati. Sudjelovao je i sudjeluje u nizu projekata, među kojima je jedan koji se vodi ovdje u Hrvatskoj u Splitu. I osim toga, još par riječi, bio je aktivan je u organizaciji raznih konferencija, događaja u ISSMGE-u, koji se tad zvao malo drugčije. U vrijeme ovog potresa 1998. godine je bio predsjednik komore Turske i dalje radi na ne samo ovim konferencijama koje su ovdje navedene. 10 godina je bio sekretar, tajnik Evo, Professor Atilla Ansal, please continue with your lecture.
Ladies and gentlemen, I'm very honored to be here. I'm very thankful to the Croatian Society of Geotechnical Engineering for inviting me or for selecting me to deliver 15th Nonveiller Lecture. But when I saw the last picture in '98, about 10 years ago, I was much younger, as you see. Years sometimes affect us, unfortunately, even though we may want it or not. Today, I would like to talk about what we have experienced in Istanbul and how we approach the problem. As an engineer, we always have enormous problems in front of us, and the questions we have to ask, for example, what can we do? So, the first question that I would like to answer is, why do we need microzonation? The purpose of the microzonation, of course, is to minimize the damage, the eventual purpose. But microzonation is a geotechnical and geological issue. First, I would like to demonstrate what I mean by microzonation. That means the earthquake characteristics that are affecting our structures are changing based on the geotechnical conditions, based on geological conditions within very short distances. So we cannot take Zagreb or take Istanbul, for example. We cannot design everything with the same level of earthquake input. So what we did, we were lucky. Sometimes you are unlucky if you have a large earthquake, like '99 earthquake, but you are lucky as an academician because then the government agrees that earthquakes are important and they try to invest in research, in applications. For example, this is one of the results of the '99 earthquake. We convinced the municipality that Istanbul is next on the line. I will show you, but I would also suggest at this point of time that if you haven't seen Istanbul, you better see it quickly. Because next time, I don't know. So this shows the first microzonation section of Istanbul done by our Japanese colleagues. Oyo actually did professionally, and this is an area you can see from the Eminönü, where Topkapı Palace is located, all the way to the airport, those of you who have been to Istanbul. And we have a mesh size of 250 by 250. We drilled around 3,000 borings, and we did extensive amount of geophysical and geological investigations. And for example, this is the mesh size. We have around 2,900 meshes, and we have geotechnical data in all of them. In addition, we have what we call a rapid response network. That is a strong motion located on the free field that would record the earthquake in cities like Istanbul. As you may know, the population of Istanbul is now 16 million. It's going to be 20 million in 5 years. So one of the big problems is that as soon as we have an earthquake, we have to point or we have to locate where is the highest damage so that teams, rescue teams, can go there. In Istanbul, we have a very large area, as I will show you a little bit later. And of course, the rapid response network, we have around 200 stations distributed all over the Istanbul. The data will come, and in 5 or 10 minutes, we will be able to understand. Of course, we have the building inventory also. We will be able to understand where is the highest damage, and so that we can send our rescue teams there first. So if you look here, we have one advantage of this. Even though we were lucky, we recorded some earthquakes. As you see, this is one of the early earthquakes in 2008. As you see, even though there is about 55 stations in that area, but all of them do not operate all the time due to many different factors. But you would be able to see even the accelerations are low. They are changing from one location to the other, and the distance between these instruments is not more than 1 kilometer. Now, this is the other one. It's a distant earthquake of a larger magnitude. But you can still see that there's a significant variation in east, west, north, south from one location to the other. And this was the latest one. It is the strongest earthquake that introduced or excited around 2% milli-G or 2% G in the bedrock elevation. And you can see that the variability is still existing. On the other hand, if we look at them, we can see that by using a very simple site response model, shake, those of you who are involved in soil mechanics may have an idea, and you can see that if we know the soil profiles as we do, we can automatically model or predict what may happen in the long run. Here are some of the results in east, west, north, south direction of the strongest earthquake, and you can see that modeling to a certain extent within the engineering approximation can take care of what may happen in the long run. Now, in terms of spectra, the spectra is one of the things that we use for designing our buildings, acceleration spectra. The simplest approach is based on acceleration spectra. These are the variability in acceleration spectra during the recorded last earthquake. You can see acceleration spectra varies significantly from one location to the other, which indicates that we have to design the buildings accordingly. What can we do? If you look to our model, the simple one-dimensional shake, you can see that we can model to a certain extent, of course. You have to always remember there are uncertainties in the soil profile, there are uncertainties regarding the model that we use to analyze, but eventually we have some engineering ballpoint. And here, in 3 locations, you see the predictions, or the modeling, not predictions, the modeling is within the engineering approximations. Now, why? Sonia showed you some pictures from the Gölcük. I will show you some pictures from 99 earthquake too. This is the Gölcük area. You can see that most of the buildings is almost completely demolished. The second picture shows you that the damage is significant here in the section, but in the other sections, it is not so significant. It is maybe due to the design of the building, which I don't think. It's most likely the changes in the site conditions. And one more time, if we go, then you can see the center of the Gölcük. You can see that newly built mosque or newly built building and the mosque survived, while all other buildings, which were like 4-story, 3-story buildings, demolished completely. So site conditions actually played a very important role. Now, if we go to one more picture, now we are in Adapazarı, you can see the same earthquake, almost same distance, but there is no damage. The reason that there is no damage is not because the buildings are built better. It is because the site conditions, to a certain extent, minimized the earthquake input. So what can we do? Now, some people may believe that I'm just talking about small earthquakes, but let's go to look to Japan. One of the big earthquakes in Japan, 6.8, and you can see now Japan has million instruments. In Istanbul, we have only 150. In Japan, they have in the order of 2,000 strong motion stations, and also downholes, as we had. And you can see that this is one of the earthquakes. If I enlarge the picture, you can see that the peak accelerations actually are varying from one location to the other. And if I build one more time, you can see that they are changing radically from one location to the other. So somehow we have to analyze the site conditions and make sure that everything is okay. Now, one of the things that we had in Istanbul after the earthquake is that we had vertical arrays. That means we have a very detailed soil profile. We measured everything almost that can be measured in the laboratory and in the field. The idea is to see how it is affecting. We now have 3 vertical arrays. That means we have instruments, for example, 140 meters, then 75 meters, 50 meters, and on the ground surface. You can see the amplification of the earthquake waves starting from the bedrock, going all the way to the top. This was a vertical array where we had the soil thickness around 140 meters, and now we have another one which is actually deeper, and it starts from 288 and it goes all the way to the ground surface. As you can see now, the predominant period shifted significantly. Now we have a predominant period in the order of 1 second, Since this earthquake is coming from 180 kilometers away, the high frequencies are lost by the time they reach to Istanbul. Now, we can see from these small examples that site amplification is a fact. We can measure it. Now, how are we going to deal with this problem? So what are the basic factors? And how can we proceed? So one suggestion from here is that let us look at the general picture. In the general picture, we see that we have a bedrock, and it ruptures somewhere, and then all the waves travel to the soil layers, and we need the motion on the ground surface in order to design our buildings sufficiently safe enough. So taking this into consideration, how can we proceed? We are interested, first of all, what is going to be the rupture, and where it is going to be the rupture, and when it is going to be rupture, but that problem is a very ambiguous problem. We can only use probabilistic approach. We cannot predict the earthquakes, but we can come up with a probabilistic approach based on the history, and we can come up with logical numbers that would affect our area in the long run. Now, here there is 4 levels of analysis. First is regional hazard. What I mean by regional hazard is something like this. This is actually a regional hazard investigation conducted by Professor Erdik and his colleagues, and this hazard should be in the order of 1 to 5,000 or 1 to 10,000 maximum. The idea is to determine, for example, in this case, variation of these spectra, design spectra, uniform hazard spectra we call it, uniform hazard spectra on the ground surface, so that we can design our buildings according to that. And as you see in this mesh in the Bakırköy area, it is 250 by 250, and it is changing every 250 meters. So in order to be on the safe side, to build new buildings or to assess the vulnerability of the old buildings, which is also very important in cities like Istanbul and in Zagreb, where you have large number of old buildings. So the idea is we should be able to have this uniform. This is a uniform hazard spectra on the outcrop, on the bedrock, obtained by a probabilistic hazard study conducted by normally engineers and seismologists. Now, the other issue that takes into our field is site characterization. As a geotechnical engineers, we have to take care of the site characterization. That means we have to have the properties and thickness of the soil layers, dynamic shear modulus, variation of shear modulus, and of course, the bedrock. The depth of the bedrock for us in terms of earthquake engineering is a very important issue. And if you look at typical soil profiles, you can see that we go all the way down until we reach the bedrock based on borings or geophysical tests, so that we know, for example, here we have, these are some of the borings in Istanbul. Here, as you can see, some of them is 90 meters, 110 meters, and even 160 meters. Of course, we didn't drill all the way to 160 meters. In few occasions we did. But you cannot do that. It's a very expensive, very time-consuming. But you have geophysical investigation techniques. The top part, the top 30 meters or 40 meters, can be determined based on borings. Has to be determined based on borings. Now, if you look here, this is a typical profile, and this is actually what we mean by degradation curves. You have to determine the degradation curves for dynamic shear modulus and damping. And as a result of that, then you would be able to analyze how the soil layers would behave during a possible earthquake. Now, the last part is 1D site response analysis. This is the simplest approach. Of course, we can do, if necessary, 2D or nonlinear or effective stress analysis. But 2D total stress analysis would be sufficient in most cases, like in Istanbul. We modified the SHAKE program that was produced in 1970s in University of Berkeley. Was very efficient program in 1970s, but since then we have learned many things. And one of the things that we have learned that the site amplification is a function of the frequency of the earthquake. So now we have to modify the program, take an empirical approach that was developed by Japanese colleagues and insert it to our program, and we also modified the program to be more stress dependent. Now, how is the result? This is the recorded motions in Istanbul during the 1999 earthquake. And here, if we go, we have 4 stations. At that time, we had limited stations, and we recorded, as you see, the maximum of 17% G. And we had damage in Istanbul in certain areas. Now, this is the profiles for 3 stations that I mentioned, vertical arrays, or at that time we had surface ground motion recorders. Then we try to see what is happening. This is actually what is recorded during the earthquake. When we use the classical shake without any correction, we'll get some fit. As you see in the north-south, the fit is not so bad, or modeling, but in east-west it is not so good. So we improved, we made it, included stress dependency into the program, and our fits have improved. We added the frequency dependence, our fits improved more. So that means even in this case, when we have the bedrock motion somewhere in Istanbul, we modeled how to get the ground motion at the ground surface, and you can see with the available 1D simple shake model to urban planning. To put our important structures in, would be able to comprehensive assessment of the building vulnerability. Now, there are a large number of microzonation research papers published everywhere. And they have taken different properties, for example, with respect to peak ground acceleration, with respect to Arias intensity, or spectral intensity. All have been tried by different researchers. We adopted a different procedure, slightly different procedure. First of all, we thought that we need to combine 2 factors. The first factor is a very empirical ground response analysis that was conducted by Borchert and his colleagues. It is based on VS30. VS30 is the average shear wave velocity at the top 30 meters. You take the layer thicknesses and the velocity of each layer and take the weighted average, and you come up with a number. And this is what is being used in Eurocode, what is being used in NEHRP, and in some of the codes in other countries to determine the site effects. So this is an empirical procedure, but it is based on actual data observed in California, based on the instrument recordings, and based on the VS measured. So there's an empirical correlation, even though it has some irregularities when you apply to the site conditions, as I showed you in the beginning. The second one is the site response analysis. Site response analysis is a mathematical tool. It has certain advantages and certain disadvantages. All numerical tools are a function of what you put inside as a parameter. And sometimes we may not be putting the correct parameters. So therefore, it has to be included somehow. We took the spectral acceleration from 0.1 second to 1 second. This is where most of our buildings are. And summed that up and actually used both parameters in a manner that is justifiable. So that we were, as I will show you a little bit later, we overlap these 2 maps and come up with a final microzonation map. But there was one other problem if you use one parameter and absolute values, because microzonation is not going to be used by civil engineers who understand earthquake engineering and who would know what PGA would mean, but it is going to be used by city planners and architects. I love architects, but architects have a limited knowledge about earthquake engineering, which they should have in the long run. So we decided that instead of giving them numbers, we should give them some limits. And here, in terms of cumulative distribution, for example, this is the average spectral acceleration that we compute from site response analysis. We divide it into 3 parts. Zone C, which is the dangerous part. Zone B, intermediate part. Zone A is the most safest part. So if we do this, for example, if we take one part of Istanbul, this is a pilot study that we have conducted. This is Zeytinburnu, one of the very close to the Eminönü, and it is very dangerous area because if we have the next earthquake, this is one of the areas that is going to be damaged significantly. And what we did site response in each cell. And as you see, when we did site response analysis, we use a lot of records, as I will try to show you a little bit later. We use a lot of records so that we make sure about the variability of earthquake input. And here we have drawn the average and drawn a best fit and used that area, that curve, that spectra as the output. Here, with respect to these two parameters, on the left you can see that we divide according to the VS30. The whole Zeitenbrunner can be divided into two categories because the difference is not so significant. So we have good parts and bad parts. But in the case of site response analysis, we have three parts, A, B, C. What we propose is to join them, overlap the map, and here we have the final microzonation map for Zeitenbrunner. Zeitenbrunner is composed of 231 meshes of 250, 250 in size, so that we can play with that with other parametric studies. What I want to show you, what is the importance of the microzonation with respect to the material parameters involved. This final result involved using 22 records for each cell, and we had borings in each cell. So this is the final version of the microzonation for Zeitenbrunner. But before Zeitenbrunner, you can see that here the importance of site investigation. On the left-hand side, you see we did a microzonation in Zeitenbrunner before all these microzonation study Istanbul was conducted. It was based on limited number of borings and limited number of input motion. But you can see that with the age, with the increase, even the geotechnical data in both are same, but the increase in the input acceleration during the site response analysis would make a significant difference. And the other issue here is that if we have much more detailed site investigation, the situation changed also radically. Now, one of the problems is the vulnerability or the return period, the frequency. Normally in the buildings we design with 10% probability of exceedance in 50 years. That means the return period is 475 years. But sometimes as a result of the electronic devices that we have in the houses or the hospitals or the schools, we cannot live with that return period anymore. So one option for important structures is to go to 2% exceedance in 50 years, which is corresponding to 2,475-year return period. And if you see, when we do the zonation, by increasing the return period, we have a different zonation. So therefore, as a city planner, you have to take into consideration what is your goal. Do you want to actually lead to normal buildings, or would you like to be interested also in high-risk buildings? And here, as I show you, if you choose different parameters like spectral accelerations or PGA or PGV, your microzonation maps will be different, especially if you take into consideration the peak ground velocity, which is one of the controlling factors that control the damage of the lifeline systems. You should be taking into consideration maybe PGV microzonation. Now, this is the end result of the OYO study. As you see, with respect to Istanbul, with around 3,000 borings and 3 years' work, we come up with a microzonation map of Istanbul in terms of three categories. The red zones are the dangerous zones. So if you have a school or a hospital in those zones, they have to be retrofitted, they have to be controlled. If we are going to build anything there, it will be designed very carefully, taking into consideration possible effects. For example, in Turkey now, all the hospitals are being built on seismic isolators. We can also plot PGA. This is the result of the PGA, and you can see that PGA goes all the way from 0.5 all the way from 0.7 to 30%. So the scatter or the variation of peak ground acceleration within the city can be radically different. Now, what is the end result? What am I going to do now? Now, the damage scenarios is, can I make an estimate of what may happen to Istanbul? Now, of course, we have seen earthquake source characteristics, site response, and now the structural features. we have to have a building inventory, and we have to have a vulnerability relationships. Now, we had about, this scenario was conducted way back in 2005 or 6. We had a building inventory based on structural systems, the age, number of stories. It's a very simple building inventory. We can improve, or we are improving the building inventory, because that will determine our vulnerability. Here, the types are limited, reinforced concrete or shear wall building or prefabricated buildings. With age, we have, with number of stories, we have from 4 stories, more than 8 stories. And of course, with respect to construction year, at one point of time in 1973, we had an earthquake code, so we considered that as a division, and we have established also post-construction 1980, we had another earthquake variation in the earthquake code. And if you do that, at that time we had a limited number of, these are reinforced concrete buildings. We had around 562,000 buildings. It was distributed, as you can see. Now, within the city, they are located like this. This is the Istanbul big metropolitan. Now, the mesh size is 500 meter to 500 meter. You can see that in some locations, we have a very dense settlement. And now, let's see what happens. So first of all, we have to have a damage scenario, taking into consideration all the capacity spectrum, inelastic deformations, and then we utilize the cumulative and discrete damage, and we classify the damage into 5 categories: no damage, slight damage, moderate damage, extensive, and collapse. And this is some of the vulnerability curves that we used to determine these vulnerability curves. Of course, changes from the building type to the other building type. And you can see here low-rise RC buildings and low-rise post-1980 buildings. So the vulnerability, depending upon the selection, changes. And at this point, we had a big project with European project. It was related to the earthquake scenarios in Istanbul, and we had a colleague, INGV, so we made a deterministic study. This is what may happen to Istanbul. As you have seen, now we have 2 faults that is not broken yet. The problem in Istanbul is that last time, in 99, it almost broke all the way to here. North Anatolian fault is a very well-behaved fault. It started to rupture from eastern Turkey in 1938, and since then, it is rupturing toward Istanbul continuously. The last rupture was in 1999. So they estimate that in the next 30 years, starting from 1999, that we may have an earthquake. And it may be a major earthquake. So this is the 2 big faults. And let's see what happens. This is a mathematical modeling of damage scenario in a deterministic manner. So you can see now this rupture, of course, there are very irregularities or unknowns. We may know that this fault is going to rupture, but where is the rupture going to start? Let's assume it started on the very west and propagated toward east. As you can see, these are some of the mathematical results obtained. The mesh is 5-kilometer mesh. You can see how the earthquake excitations would change. What happens if it breaks in between? It's a biaxial rupture. And here you can see the variation of accelerations in different parts of the city. And this is, again, uniform rupture now toward west. And you can see that depending upon the rupture, things can be radically different. Now, this is one of the results of these, one of the worst results from these scenarios. And you can see that this is the spectral accelerations at short period, and as you may be able to read, it changes from 3G all the way to 0.5G. The design code in Istanbul, spectral acceleration-wise, until this year, has been only 1G. So you can imagine what may happen if we have this earthquake. And here, this is the number of collapsed buildings in each square within the city. And this is going to be like 160,000 buildings, 10,000 medium, 4,000 extensive, 91 will be totally collapsed, and it is estimated that we will have in the order of 150,000 casualties. Now, how can we do that? So we have to do a lot of parametric study, and we developed a model called koji loss. Of course, now they have a better version, and it starts taking into consideration the seismic hazard and geotechnical conditions. It inputs the earthquake characteristics ground series. Then we develop the new herb envelopes, and then we determine the microzonation maps, and then based on the building inventory, we can determine the damage distribution. This is a computer program that doesn't require something new. It is a very simple programming skills, but now we have, of course, everywhere in the world, they have a lot of programs. Here, one example. We did a very detailed study in Zeytinburnu, the city I showed you previously. And here, we have a very detailed building inventory. There was about 16,000 buildings here. All of them were evaluated in a very detailed fashion, even on a building plan. And you can see that we have the B represents masonry or reinforced concrete. And if we do the damage study for Zeytinburnu, you can see that we will have some areas which will be very susceptible to high damage. In Istanbul, in Turkey now, we have a rehabilitation law. That means if your house is somehow considered vulnerable during an earthquake, the government has all the power to demolish it. So a lot of old houses or vulnerable houses are being demolished in Istanbul, and new ones are built. Of course, between you and me, I'm not very sure if we are building safer buildings. And here, based on the 16,000 buildings, the damage was like 2,444 collapsed buildings. And that is relatively high if you consider that the total number of buildings is 16,000. Now, as a last item in this probabilistic study, the procedure I explained is always in terms of site response. There is always a faster procedure, and this is based on VS30. This is the NIHERP procedure. And if you look at the both of them together, that NIHERP, the simple procedure, is not giving very high results. So it may give a false feeling that you are on the safe side. But it is necessary to take into soil conditions into effect, and it is necessary to take possible earthquake characteristics variability so that you can have a better understanding. So this is what I was suggesting. Earthquake-based regional scale is very necessary. Large number of hazard-compatible. Somehow I seem to have jumped over them. Large number of earthquakes. Since I may have some time, let me go back. I think I jumped over some of my slides. Where are they? Oh, here. Now, this is an important part of the microzonation, which I forgot. I don't know how I jumped over it. When we are dealing with number of earthquake inputs to do site response analysis. In some earthquake codes, you are only required to select 5 input motion. But here, we did a parametric study. We selected, as you may see, 5 input, 10 input, 15 input, 20 input, 22 our design, and 25 input. As you can see here, with the increase of the number of inputs, you get an average which is much more representative, taking into consideration the variability of our ground motion. If we go one step, this is, for example, the input ground motion that we selected for site response. You can see the variability of the recorded motions. These are from all over the world. What we mean hazard compatibility is they are from the same rupture type, same distance approximately, and same magnitude range. And if we want to go one more step, you can see we have to also do scaling. Take the record from anywhere else, which fits to this hazard compatibility, and then scale it such that the black line is your target spectra that you obtain, or outcrop spectra, but you have to take that into consideration to do site response analysis. And you can see the best, we also try different scaling procedures, and the most appropriate scaling procedure, which is also suggested in ASC 7, is to scale each record to fit the target spectra using an optimization technique. So this is one way of doing a site response analysis, taking into account all the variability, all the possible variability that may occur as a result of the earthquake input. And as you can see, if I plot them, they are all slightly different. Now I go to my last slide. And here, large number of earthquake inputs are important in one sense, as I demonstrated, and large microzonation with respect to average spectral accelerations and site response analysis is appropriate system. 3 relative levels, high, medium, low, is understandable by everybody. Detailed site characterization is a very important issue. There are differences between Nieherr formulation, this VS30, and there can be significant differences among the probabilistic and deterministic scenarios. So with this, I go to acknowledgements. There has been many people who worked on this project, and I would like to express my gratitude to them. And my last slide, the end. Thank you very much.
Thank you very much, Professor Atilla Ansal, for this very rich and interesting presentation. I would like to call for questions for Professor, if there are any from the audience. Please go ahead.
My name is Pierottijevoj. Just one question. You showed us this. My name is Pierottijevoj. I'm just asking about the correlation between the geological composition and the vulnerability. It's usually somehow coupled with this, I think. And I do not recall whether you mentioned this depth of bedrock and big ground acceleration in the area of Istanbul. What is the geological composition of Istanbul? Did you find some correlation between geology and vulnerability?
It is very difficult to find a direct relationship with geology, because in order to have a relationship, we have to express geology in terms of numbers. And geological formations are there, but one issue in terms of establishing, even though empirical relationships, you have to have numbers. We have established, as you have seen, that based on the average spectral accelerations in each location, you can come up with the possible damage scenarios. For example, if I go back to these curves, which are our vulnerability curves, you can, and maybe I go one more slide, you can see that we determine the spectra on the ground surface, elastic acceleration response spectra, and correlate or determine our damage scenarios or vulnerability with the inelastic spectral displacements. We have the spectral displacements at each location. This is also for rapid response. With the earthquake records we obtain during a possible earthquake from these strong motion stations, we come up with the spectra at each location. And from these response spectra, we determine the displacement, inelastic spectral displacements. And with inelastic spectral displacements, we come up with the damage. As you see, on the horizontal axis, we have inelastic spectral displacements. So depending upon the spectral displacements on the vertical axis, we have the damage ratio. So the controlling factor is inelastic spectral displacements. So from the geology, starting with site response with geological inputs, we get on the ground surface inelastic spectral displacements. So this is the correlation. There is no direct correlation, but inelastic displacement, spectral displacements, is a measure of what is happening in the geology and geotechnical site conditions.
Thank you.
The reason I didn't mention, I don't believe in it.
Thank you.
Now, because all this classification, it is engineering-wise, of course, a very practical tool. Especially for structural engineers, they don't really need geotechnical engineers anymore. They look at the VS and they decide. But this is not really very correct. What I tried to show you, that VS 30, which is measured and considered at the top 30 meters of the soil layer, can be approximately correct in certain locations when you do not have very deep deposits. Like I showed you in Istanbul, near the seaside, we go all the way to 300 meters. I was in Bucharest last week, and they told me that they don't have a bedrock. The bedrock is somewhere 3,000 kilometers down, 3,000 meters down. So the thickness of the soil deposits cannot be, or the properties of the soil deposits cannot be defined with one term, VS30. And NIHRP and site classification and Eurocode and Turkish code and American code actually takes this VS30 and classifies the soil as ABC. It is practical, but applicability is questionable. So I don't really believe very much in the soil classification in the Eurocode or in American NIHRP. It is, if you have a very standard deposit, consider a city which the thickness of the soil deposit varies from 30 meters to maybe 50 meters, then it works. That question is not an easy question. Of course, as is, we considered. But now we are considering the vulnerability at that time around 500,000 buildings. And with 500,000 buildings, you do not really have a very detailed information sometimes. Just it's a street survey. And as you see, when I showed the building inventory, I showed that in terms of three factors: height, or number of stories, number of years it was built, and of course, if general type, reinforced concrete or masonry. You can go into much more detailed vulnerability analysis, and it has been done in many places by many researchers. You can take the building, take its general plan into consideration, take its frequency into consideration, take all its structural features into consideration, and determine the vulnerability. That would be perfect. But in a city like Istanbul, where you have, now we have around 2 million buildings, there is no way we can come up with a very accurate data concerning the 2 million buildings. Even at the time when we had only 500,000 buildings, it was not really possible. You have to make some simplifications if you want to have an answer. Otherwise, you have no answer. Of course, you're right. Vulnerability is not only based on these three parameters. It can be many factors. And there are lots of research, lots of papers published on vulnerability relationships concerning different types of building, different types of construction. If you don't have any questions, I want to show you one more thing. I forgot, because Sonia asked me to also talk to you about the earthquake engineering, but then we jumped over the earthquake engineering because she started with the first one. So here I want to show very briefly what is earthquake engineering doing in recent years. Oh, come on. European Association of Earthquake Engineering was established in 1964 when we had the big Skopje earthquake. At that time, we had three guys who started here, as you see, Medvedev, Bubnov, and Ambrasis. Unfortunately, all of them passed away. We also had Bubnov, I think he was from, yeah. But later, and since then, we established the first conference, and now we are having conferences every 4 years, and every 8 years we're having joint conferences with seismologists. So we are having every 8 years. The first one was in Geneva. The second one was in Istanbul. It was called European Conference on Earthquake Engineering and Engineering Seismology. And the next one is going to be just earthquake engineering, and it's going to be in Thessaloniki. This is the present executive committee at the moment. And we have 31 national delegates, including Croatia. And we publish, and of course, I must thank Professor Drazen Anijic. He forced me to be general secretary in 1994. And I served as 20 years as a general secretary. Now my first 4 years is as the president. During this period, we started to publish Bulletin of Earthquake Engineering. Now we are in the 15th volume. And as you can see now, we receive in the order of 600 manuscripts. Unfortunately, we publish every month around 20 manuscripts. So the maximum number we can publish is in the order of 240. And we are rejecting almost in the order of 60% or sometimes 70% of the papers that are submitted. We also have, as Sonia showed you, we also have a book series. We have published 42 volumes in the last 15 years. And some of them are very interesting in terms of earthquake engineering and geotechnical engineering. And I would strongly recommend that you look at them. They are mostly also available. And we also have individual members. In 2002, we started to have individual members. And in order to be individual member, you have to pay only 40 euro. And as a result of that, you have electronic subscription, reduction in the books, reduction in the registration cost. And of course, you can be a member of the executive committee and enter the General Assembly. So this is our web page. I would strongly recommend that you look at it. It has all the information. During the last 15, 20 years, I was General Secretary and President. And you are cordially invited to become an individual member. Thank you very much. So with the advertisement, I think we're finished. Thank you very much. It was very nice to be here to talk to you. And you can always write to me and ask questions, as always. And next year, I will be in Thessaloniki giving one of the keynote lectures on site response, very similar topic. There you can ask any questions you want also. Thank you very much.
We are now at the end of our 15th Nonveiller Lecture, and we would like to thank you with a small gift from Croatian Geotechnical Society and the packet of 15 Nonveiller Lecture.
Thank you very much. It is my pleasure.
So to remember all this, please take this. And will you give this? I don't want to drop it.
Thank you very much. It was very kind of you, especially Croatian Geotechnical Society and Igor and, of course, Sonia. Thank you. Thank you very much. Thank you very much.
Thank you very much. Please, you speak and take the picture. You can take the picture of it.
Yes, please. Without picture, this picture is going to go, of course, to my Facebook. One more.
Thank you very much. And with this, we are finished. So now we are finished with the official part of this Nonveiller Lecture, and I invite you for bucket and just in the room next to here. Thank you very much all for coming. I hope you enjoyed the lecture.
Was it okay?
It was perfect, as always. You are the best presenter.
Thank you very much. You're very kind.